Greetings, hello, welcome back. We're looking at example 3 on page 211, chapter 3, 4. It says to solve an exponential equation, and they're given to us 4 times e to the 2x minus 3 equal to 2. We're going to solve this algebraically. Of course, we're solving for this x here. And so we understand we're going to have to use, because the base is e, we're going to have to use a natural log. So we go through our steps algebraically, isolating that x. We're going to add 3 to both sides. And we get 4e to the 2x is equal to 5. We want to isolate the e initially. We're going to divide by 4. And e to the 2x is equal to 5/4. So in order to get rid of the e and isolate the power, we need to take the natural log of both sides, because that's our inverse operation to get that e to disappear. So the natural log e of e cancels. We're left with 2x on the left and the natural log of 5/4 on the right. And we know that we just want x. We're going to take both sides and divide by 2 or multiply by 1/2, natural log 5/4, and we can then use our calculator to come up with that approximation, 0.11. Go ahead and try problem number 61 and come back here for the solution. And in problem 61, we're being asked to solve the exponential equation, just like we did in the example previously. Round your result to 3 decimal places using your calculator. So again, we're trying to isolate our exponent, and this time it is a negative x value. So using properties of algebra and solving for e initially and then its exponent, we get e to the negative x is equal to 3/5. When I simplify the right hand side, again we're going to take the natural log of both sides, and that leaves us with negative x equal to the natural log of 3/5. Now here we need to multiply both sides by -1 to solve for positive x. X is equal to negative natural log of 3/5, and using our calculator we can solve that and approximate to the nearest thousandth, or 3 decimal places. Another way of looking at solving this function is to set it equal to 0 and use our graphing calculator for clarification. So what I've done here algebraically is to subtract 2 from both sides, and then we have an equation that we can substitute in to the graphing calculator. Let's look and see how that works. Here I've plugged in the function for e to the 2x minus 5, and we can see the graphical interpretation of that. One of the ways that the book suggests is to find the root or the 0 and use the calculating feature. So we're going to go down to option 2, calculate that 0, which is, of course, our solution. It always says left bound. We know that we're going to be to the left. If we were riding this roller coaster, we're on the left hand side of that intersection. And then it says, of course, we want to go to the right bound. So we're going to use the arrow, move over to the opposite side, or the right hand side of that intersection. The guess is 0.3 and 2.3. The actual 0, when y is 0, x is 0.112 if we rounded that to the nearest thousandth. I'm going to go over example 4 on page 212, solving an exponential equation. We have the function 2 times 3 to the 2t minus 5 minus 4 equals 11. And what we're going to do is, solving algebraically again, reduce to just the base and the power. So we're going to add 4 to both sides and divide by 2. And that would give us, add 4, thank you, divide by 2, 15 halves. So we end up with 3 2t minus 5 to the power 2t minus 5 equaling 15 halves. So the thing that dictates our next step is the base on the left. We have the base 3 raised to the power 2t minus 5, and we're going to take the common log base 3 of both sides. Common log base 3. And on the left, log base 3 of 3 just leaves us with that power. We get 2t minus 5. And on the right-hand side, we get the common log base 3 of 15 halves, or 7.5. And we could take this problem all the way, but right now we see that adding 5 to both sides and dividing by 2 gives us our solution, and that's just a simple problem to plug into the calculator. They come up with an approximation t equaling 3 and 42 hundredths. I'd like you to try problem 65, and then we'll move on to example 5. Problem 65. So problem 65 is very similar to the one that we just did algebraically. We're going to be adding 13 to both sides and dividing by 2, leaving us with 2 to the 3 minus x equal to 113. 113. I did it again. Didn't leave enough room. 113 over 5. On the left-hand side of our function, we have base 2 raised to a power, so we're going to take log base 2 of both sides. Log base 2 of both sides on the left-hand side, canceling, leaving us with the algebraic expression 3 minus x. And we can do one of two things. I'm going to do this just to change it up a little bit. I'm going to add x to both sides and subtract log base 2, 113 fifths from both sides. So it would look like this. Log base 2, 113 fifths, 3 minus that is equal to x. Again, we're at the point where we grab our handy-dandy calculator, and the book comes up with approximately 1.498. X approximate to 1 point, that's negative 1.498. Let's just move right along looking at example 6, I believe. Example 5, excuse me. Says, solving e to the 2x minus 3e to the x plus 2. And what they want you to see here is that we have an exponential, a quadratic function. So they rewrite it like this: e to the x squared minus 3e to the x plus 2. And you can see when you rewrite it like this, we have a power of 2, a power of 1, and a power of 0. And so that should put up a flag for us. We see that we could possibly factor this. And when we think about this, e to the x squared, if I factor that, we get e to the x times e to the x. That's e to the x squared. Then we're looking for factors of 2 that add up to negative 3. Factors of 2 that give us this midterm negative 3. We know that is minus 2 and minus 1. And we have successfully factored. What we're looking for are the two solutions where either one of these factors is equal to 0. We understand e to the x equals 1, gives us one of those, and e to the x equals 2 gives us another So in the case of our first solution here, e to the x equaling 1, we're going to take the natural log of both sides. Natural log e to the x gives us x. And the natural log of 1 is saying e to what power is 1? And we know anything to the 0 power is 1. In the second possible solution, we're going to do the same thing, taking the natural log of both sides. Natural log e to the x leaves us with x. And then the other solution will be the natural log of 2, which is approximately 0.69. Now the other way we can look at this is by studying the graph. I've put the function, gotta use the mouse. I placed the function into our graphing calculator, and we can see from this graph we do indeed have a 0 here at 0 and roughly 0.7 when we put the function into our calculator. Another strategy we find at the top of page 213, it says solving logarithm equations. You can write it in exponential form, and they give us the example natural log x equals 3. We remember our inverse properties. If we raise both sides as a power of, I'm so sorry, that was a 3. Natural log of x equals 3. If we raise both sides of the equation as an exponent of e, we're using the same exact operation. And what it does on the left-hand side, e to the natural log base e, those are inverses of each other, and we solve and get x. And then we can see on the right-hand side in exponential form e to the third power, which is just simple calculation on our graphing utilities. Let's look at example 6 together. It says solve each log equation, and we have natural log 3x is equal to 2. Well, following what we just did, we can see that exponentiating, raising each side as a power of 2, leaves us with 3x is equal to e to the second power. X is equal to e to the second power divided by 3, or 1/3 e to the second power. The second part of that is as straightforward. It gives us log, common log, base 3 of 5x minus 1 is equal to log base 3 x plus 7. And we understand that if we write the original, they are 1-to-1. We have the same thing on both sides, log base 3, so that we understand 5x minus 1 is equal to x plus 7. As long as these bases are the same, we're good to go. So solving that, we get, subtracting 1x from both sides, we get 4x. Adding 1 to both sides, we get 8. Solving x equals 2.